Welcome back to another episode of One Wingspan Above, where we discuss everything to do with ground effects. Today we have a very special episode for you where I interview Billy Thalheimer from Regent, who are developing the Seagliders. The Seagliders are very interesting machines indeed. They have blown wings with 12 props. They take off on hydrofoils. They have surface-piercing hulls. They've got a box tail, and they're made out of composite. At the moment, they are testing the Seaglider. They have been floating them. They have been foiling them. And at the moment, they're trying to fly them. So they are very structural in their testing to make sure everything goes smoothly and safely. I asked Billy about safety because that was my main concern, and I just realized during the interview or after the interview that I've been kind of approaching the Seaglider from the wrong angle. Myself, I was more thinking about the Seagliders being full-on ground effect craft. In essence, they're not. They are actually more like water planes with hydrofoils on them. Since they have very skinny wings, high aspect wings, even though they're blown wings, they never really get into the chord-dominated ground effect, and hence you can compare them more with water planes. Water planes have successfully been taken off and landing off water for many, many decades. It soothes my mind that I can compare more with water planes rather than ground effect planes, ground effect craft, with respect to safety. The only kind of concern at the moment is that moment where the Seaglider goes from foiling to flying. And Billy kind of touches on some points there. I've asked him some questions. So enjoy and see what you can get out of it. If you have any comments, questions, ask us those comments below, and I'll try to answer them as good as I can. For the rest, just enjoy this interview and see you next time. Thank you very much for joining me after this little while.
Long overdue. I know we've been sort of, chatting back and forth. I know you've been, doing your own sort of work analysis on the concept, which is awesome for a few years now. So it feels like this is long overdue. It's great.
So welcome. Great to have you here. And Regent is one of the most exciting companies in transport technology right now. Because of the first time in history, it feels like ground effect is actually scaling, not just as a curiosity, but as a real commercial success. So you've done an incredible job building the narrative around float, foil, and fly, which captures the transition beautifully. But so far, the technical side of that last step, the fly, has been under wraps a little bit. So I'd love to start there if you could. Regent manages that transition from hydrodynamics to float and fly. How is that done? And especially now that you've proven it at quarter scale.
Yeah. Well, thanks for having me, Paul, and excited to chat about all things ground effect and wigs and Seagliders here. So that is really the key part, right? Is that transition from foil to fly. There's lots of hydrofoiling boats out there, lots of aircraft, even past wing and ground craft, but no one's done that sort of elusive foil to flight transition, which really underpins the whole Seaglider technology and gives us the wave tolerance of the hydrofoil with the speed of the wing. A few different parts to that transition. The historical problem is that foiling has a limited top speed, and of course Seagliders use the hydrofoil for the wave tolerance. That's, in our opinion, one of the main challenges that has really precluded wing and ground craft and even flying boats and seaplanes, etc., from scaling around the world is that poor wave tolerance. So you can't operate them in open waters and can't rely upon them for critical missions. So the hydrofoils unlock wave tolerance. We get 5 feet or 1.5 meters wave tolerance on our hydrofoils on the full-scale Viceroy Seaglider. Hydrofoils have a limited top speed. Water's about 800 times more dense than air. If you push a foil really fast through the water, you get a phenomenon called cavitation, which is where the suction side of the foil actually ends up boiling the water and you lose all your lift. Add that to the incredible difficulty of control in the hydrofoils. Your controls need to be far more precise because the water is so dense and you have much smaller surfaces to actuate. So fast hydrofoils are a very difficult problem. The fastest hydrofoils ever in the world are in that sort of 50 knot plus or minus range. And that is where Seagliders are operating. So first we needed a control system and a hydrofoil design to get us absolutely as fast as possible up to that about 50 knot range on the hydrofoils. Then the other side is our takeoff speed. So obviously wings need enough airflow over them to generate enough lift. Below that you get stall. And so historically, the top speed of a hydrofoil and the bottom speed of a wing stall, which are happening at 80, 90, 100 plus knots, have not overlapped. And so with the Seaglider configuration, we blow the wing. So we distribute that propulsion along the wing. We blow the high-speed prop wash over the wing. We're tricking the wing into generating high lift at low speeds. And that allows us to slow down the takeoff speed. So for the first time, we can do that foil to wing transition. Now, Seagliders are very different when they are operating in hydrofoiling and operating in flight, as you might imagine. So it'd be very difficult for any human operator to seamlessly go from one to the other. That's where our digital flight control systems come in, where in that instant of takeoff, they can switch from the hydrofoil controls to the air controls. So sort of underlying technology, it's very advanced hydrofoils and control systems. It's the blown wing and being able to slow down takeoff. And then it's the digital flight control system that we wrap around all of it to be able to choreograph and coordinate that takeoff.
So I'd imagine that you have redundancy in the system, just in case.
Lots of redundancy, riddled with redundancy. And we have to, obviously, to have humans on board. So it starts from our triple redundant flight control system, 3 different computers making decisions and voting. In our current configuration, we have 4 different power buses, 4 different redundant power buses that cross-feed to the 12 different electric motors and propellers on the wings. So they're cross-linked. We can continue flight with about half them gone, and they could glide into a landing with all of them gone. So incredible redundancy there. And then if you look at the configuration, we have 2 sets of flaps, so actually 4 moving surfaces. We also have 4 moving elevator surfaces on the tail. We have 2 different rudder surfaces. In those cases where we have single surfaces, we have multiple actuators. So from the flight computer system to the propulsion system to the actual surfaces, the moving actuation systems, we have redundancy throughout the whole system.
So that's a lot of actuation surfaces. The hydrofoils actuate, the elevator, the rudder, all that sort. So it's fully controllable, right?
That's correct.
So the computer actually controls the system. So I'm going to ask, what happens if the computer cannot control the system anymore? Have you got a plan for that?
Yeah, so these computer controls are very precise, and so that is why in our test campaign we continue to expand the envelope and test all these corner cases so that we are sure our controller is robust. Keep in mind that computer control is everywhere today. When you're landing on your Airbus, the computer is landing the airplane. When spacecraft, SpaceX are taking off and docking in outer space and then re-landing, that is all computer control. So as long as you have prescribed and fully explored your operating envelope, you can develop controllers, given that you have enough control authority in your system, and we do with those hydrofoil and aero controls. You can prescribe a controller and design a controller that manages the full operating envelope. So really the things that can go wrong are failures in the computer, hardware failures, which is why we have multiple of them, 3 of them that vote. So if any one has an issue, you still have 2 that can compare their assessment of the world and then what they think the Seaglider should do as a response. And then that's also why we have, you could lose power. So that's why we have redundant power systems, or you could send a command and your actuator could be broken, or your control surface could get stuck, what we call a hard over. And that's why we have redundant surfaces. So that's how we handle the failures. The software controller itself is extremely robust, and then we handle these failures with these redundancies throughout the control system.
So you're kind of hoping that
the software and the hardware will always be working, I'm assuming.
Well, I mean, certainly that is the hope and the design intent that your safety critical controls are working. This is how safety critical controls are designed throughout both maritime and aviation, right? That you have software controlling the vehicle, whether that's landing an aircraft or whether that's precisely controlling the location of a ship, so that you're drilling an oil well and don't have a deep water horizon and a massive oil spill. So software critical control systems and safety critical control are abundant throughout the world. We have a lot of the people who design and develop those on our team now. And so it's really just the implementation, the Seaglider, which is the unique aspect.
So I guess some people might say, are you not concerned about the fact that if the control system really fails, in an Airbus, you will have some backup. The pilot will be able to control the airplane. The airplane should be stable enough for the pilot to actually take control and somehow put the airplane down. Are you not concerned that people might say, well, the Seaglider and maybe other VTOL airplanes like the big drones, manned drones that they're developing now? Are you not concerned that people are saying, well, if something happens, you have no other way of getting out?
I would say thinking through failure cases and how to protect safety criticality is the base consideration in the design of a sea glider. It should be in all these cases. And with that approach, I am far more concerned about human error, flying fast and low over the waterway, mistaking something. Think of how many fly-by-wire systems and an Airbus aircraft, which are drastically controlled throughout, have actually had humans introduce error into that systems by making a simple mistake, by stalling the airplane, by confusing an angle of attack, etc. The power of humans to get confused and then to overrule a system which is actually making the correct prediction is far more proven throughout aerospace history than controls actually making mistakes themselves, particularly when there's multiple redundancies throughout. And that's why, for example, you look at the SpaceX capsules and there's no human control there. They are off on that autonomous system to do their safety critical docking, which is still protecting human life. And so in our cases, that came down to, well, what is the major driving safety concern? And as we look back through the history of the chronoplanes and wing and ground craft, but also seaplanes and things like that, it is not structural failure and not controls failure that has resulted in the most catastrophic events. It is human error. It's the focus and the fatigue of a human that is focused on controlling this aircraft, essentially landing an aircraft for the entire time you're flying at high speeds and low altitude. We interviewed them. We determined very early on that it's not a viable case. We're going to introduce great redundancies, 1 in 100 billion probability that you're going to have a failure. So that is mathematically longer than the entire life of the entire fleet of a Seagliders, right? Your 25 plus year life over thousands of Seagliders, probabilistically, this should never occur once, which is a much greater failure probability than what happens if the operator is tired that day and makes a mistake. So that's been our safety approach. We're actually leaning in on these digital systems and making sure we test them comprehensively.
There's a few phases in your flight schedule. There's the floating, the foiling, and the flying. Obviously, the most intricate part is between the foiling and the flying, I assume, because moments change once you leave the water. The whole moment system around the air, I can't call it an airplane, obviously, around a sea glider changes. So the system catches that in time, hopefully. And can you tell us a bit more about how you actually have you got anything special in the system whereby you, when the hydrofoils leave the water, when you catch that difference in moments?
Yeah, absolutely. I mean, you're 100% right. When you have foils in the water, there's drag on the foils that gives you a nose down moment if you were to draw that free body diagram. And when you leave the water, you lose that nose down moment, and then you need to generate some nose up so you can keep your keep your nose going up. So as it comes to the tail sizing and tail design, you'll notice a Seaglider has this box tail, very endemic of a Seaglider. If you look at past wing and ground craft vehicles, you'll notice this massive T-tail, and what they're doing there is they're trying to get that tail up and out of the ground effect, up and out of that very dynamic aerodynamic system going on. They're also trying to increase a lot of surface area so that when they are flying slowly, they have the pitch control. So that's why they have these massive tails. That's very heavy. That's expensive to build those big parts. We looked at that and said, how do we take a sort of a similar approach? I mean, we're not changing physics. We need to be able to control the nose at these low speeds and switch that moment on the nose to pitch up when we take off. But how do we do it in sort of a structurally efficient, compact way? We actually derived our inspiration from F1 cars that are generating downforce, but they have that box design. And so we created the box tail, which actually we now have patents for. And so that box tail, not necessarily a new concept in aviation to have a boxed wing, and actually wings get more efficient with the box. But if you look at the tail in sort of a simple way, you'll notice there's two horizontal surfaces, so sort of a biplane tail for the elevators, and then three vertical surfaces, so three rudder systems, but it's in a very compact package. So structurally, weight efficiency, it's very good. Aerodynamic efficiency, we still have lots of area, and then we can do that low speed pitch control.
Which is interesting because that brings us to the fact that the Seaglider is a different kind of design to, for instance, the Caspian Sea Monster. Obviously, the Caspian Sea Monster had very stubby wings, a very big chord, whereas the Seaglider has got very skinny wings, a very small chord. So I'm assuming that most of the regime that you're flying in is actually not in chord-dominated ground effect, but span-dominated ground effect. So I'm assuming then that tail is not that much of an issue anymore. Is that correct?
You're absolutely right that we're flying more in the span-dominated regime than the chord-dominated regime, which was important because by lifting up off the water as opposed to just a few feet, but we're actually flying at more like 30 feet or half a wingspan, we still get some ground effect, but importantly, we're flying higher over waves. We can bank the wing more, and so we're more maneuverable. If you look at the Acronoplans trying to turn, there's some great videos of some of the reverse delta wigs, like the Lippish wigs, trying to turn, and it just takes forever, and it just makes them not very viable or maneuverable. It was very clear that to make this an operationally viable concept, we had to fly a little bit higher, and therefore in that span-dominated ground effect, which is why you see that high aspect ratio wing. And moving to a high aspect ratio, we're actually able to get similar lift to drag coefficients than flying in that chord-dominated ground effect. So it was architecturally, it still made a lot of sense for us to do that.
Interesting that you take the approach that you actually have an elevator that you can actually control, or that the computer controls. Does it give you some added benefits, or does it kind of does it throw in some extra difficulties in the system?
Yeah, well, I mean, having additional degrees of control and redundancies in certain areas is always going to make it a more precise vehicle, more comfortable, able to withstand. If you look back at some of the reasons why the Acronoplans and past wigs haven't worked, their weather tolerance, right? So maybe it works perfectly in a glass, calm sea state with no wind. Introduce any wind, you start getting deviations from that basic flight profile. Flight Ship, which is one of the early reverse delta wig configurations, had a divergence in a slightly higher sea state where actually a wing gust got in under the wing. It was uncontrollable. It diverged and ended up with a casualty of the crew. And so we studied all of this. We studied, the 60 years of ground effect history before we designed, and certainly before we started testing the Seaglider. And we said that is not a viable configuration for a vehicle that goes in the real world and operates in real world weather conditions.
Yeah, it sounds really wonderful. With regards to hydrofoils, obviously you retract the hydrofoils when you leave the water, so they're up against the fuselage or the hull, I guess you can call it, because
Yes.
it's not actually an airplane. What happens when you land? Because I haven't actually seen that.
Yeah, so you're absolutely right. The hydrofoils are like takeoff gear as opposed to landing gear. So we retract those hydrofoils. We have that deep V hull shape, which is atypical. Actually, has never been used before on a flying vehicle. Historically, seaplanes, flying boats, wing and ground craft had a flat planing hull to get up on the surface and skip over the surface on a plane and generate enough speed to take off. The problem there is that you have poor wave tolerance. Again, those vehicles are largely designed for calm sea states. And so for us, we never need to plane. We get all of our takeoff speed from the hydrofoils, which are wave tolerant themselves. We retract, and then on landing, the foils do, impact the water, obviously, but they're retracted and very sturdy. They don't, if you watch an e-foiler do a backflip and land back in the water, you can see how squirrely they are as they re-enter the surface. So foils get in, they're very robust. When the water reattaches to the foil, they can actually help provide some stability through the landing. But the most important part of the landing is that we're taking the brunt of the impact on that hull. And that deep V hull can pierce through the water and shed that wave energy, so it's a more comfortable landing for the crew and also can handle significantly higher sea states.
Yeah, it's actually amazing because there's so many innovations in this sea glider. It's you are really throwing spaghetti at the wall and making sure everything sticks just about. So you got a
Well, it
box
has to.
tail, you've got the surface piercing hull, you got foils, you got the blown wing, you got uh, carbon, fully carbon fuselage. Um, how do you kind of keep track of all this and make sure it all works?
That's really it's part team, right? That we are not taking the approach that this is a boat that happens to fly, or this is an airplane that happens to operate on the surface. This is truly both. And so, half of our engineering team, first off, is software engineers, because so much of this is software controlled, the control systems, the testing, etc. But then within the disciplines, half of our team comes from the maritime world and building racing yachts, whether it's America's Cup or Sail GP, and the other half of the team comes from aerospace, whether they're writing those safety critical control algorithms for spacecraft and satellites, or they're designing aircraft or eVTOLs and they're familiar with that high power electric propulsion. Now that we're approaching production and manufacturing, we're bringing in additional team members from automotive, so we're sort of getting that third perspective, which is pretty exciting. But very important that we have those subject matter experts who live and breathe, maritime or aviation, working together, sharing ideas, because a sea glider is fundamentally a hybrid of both worlds. So that's one. Two is just in our scaled test campaign. We started small, nimble, we could tweak things. So that was our quarter scale prototype, Squire, which we're now productizing actually as a drone platform. But that's when we proved float foil fly for the first time. Actually, the thrust to weight ratio of that vehicle is pretty close to the thrust to weight ratio of our full scale Viceroy vehicle, about 35%. So we didn't want to overpower that vehicle. We wanted it to represent some of the real physics. We could practice different takeoff and landings. Learned a lot there that we can now apply, and particularly matured our modeling tool set such that we can apply that now on the full scale Viceroy vehicle. So it's crawl, walk, run, right? It's test all this out at the small scale. Now we're doing the full scale, comprehensively go and test in the foil phase, in the float phase, and then coming up in spring of next year into the flight phase.
So how did you start the design of the Sea Glider? I mean, you cannot look at other craft and just copy paste. You've got so many bits of other craft that you have to really completely start from scratch.
Yeah.
Did you just kind of just go from the aeronautical point of view? This is the airplane. Did you come from, the Russian plans and delve through the Russian literature and see what's out there? Do you go about designing an airplane like that, or sea glider like this? I still have to get used to it.
For sure. Well, we did do a very comprehensive literature review. As you would with any new design vehicle. I learned that through my academic education as an engineer, and a lot of the early team did similar. So first, we read absolutely everything there was. There's some translated, declassified Chronoplan design and learnings documents, which were pretty cool to read through. All the Lipich stuff. we read through blown wing literature. There's a lot of work done at MIT on that. You look at, the NASA X-57 Maxwell stuff. So we're able to pull, the blown wing, the ground effect. A lot of our team came from the America's Cup, so they were building these hydrofoil systems in the racing world. That sort of got us the art of the possible. Then working with some of the best, multidisciplinary optimization engineers in the world, which was also my background as well. We sort of threw all those bits at a configuration tool that we actually wrote ourselves in-house to say, okay, here are some assumptions on weight fractions and available power and how the physics of the wing works. And then we could start to, once we sort of had all of those constraints and real world variables, then we could start to sort of iterate and say, okay, now the hull's actually going to look like this, and let's add some design, and this weighs a little extra. Then you sort of follow a standard, really, aircraft development process. But from the initial days, it required that certainly literature review and then deep familiarization with, well, what does a composite hydrofoil system weigh of this size class? And it turns out the Viceroy Seaglider is very similar size and weight class to an America's Cup yacht, so somewhat intentionally, as we could draw on a lot of those learnings.
That's incredible that it all kind of fits together so nicely. So obviously at the moment you're getting into your winter season. You're still testing, hopefully.
Yes, yeah, I'll be testing all through winter.
You've proven float and foil. Unfortunately, this might be a bit of a sore spot, but in October, I saw some pictures coming along whereby some bits on the Seaglider were detached, as you might call it. Can you highlight what happened there in your own words, or?
Yeah, well, we're working through the test campaign. Obviously, safety is the very top most critical prioritization. So we're expanding as we progress through the test campaign. We're expanding the envelope, as I mentioned earlier, to fully characterize these software control systems. So as we do, this is the test campaign. This is not the product real world operating campaign. And so when you're learning to ride a bike, you need training wheels to start. You fall over, you get back on, and you learn. And so that's exactly what our team is doing now. We're ensuring that every single test campaign is fully safe for the crew that goes on board. And sometimes I am the crew that goes on board, my co-founder the crew that goes on board. So we're absolutely putting that safety criticality, we're internalizing that and getting on board ourselves. In that test, we expanded the envelope in a new way. We learned a lot about the vehicle. We're actually using that to build some new parts on the vehicle to modify some of the software controls. So anytime you have an event, particularly if you're expanding the envelope, particularly if you take damage, you just uncover a treasure trove of new data. And so all of that is helping us mature from the prototype we have on the water now to that full-scale vehicle, to the product vehicle we'll be delivering in 2027. So team is back on the water now. We recently did a medevac demonstration for our Marine Corps customers. We will be, progressing through our test campaign again. We're switching out some parts on the vehicle over the course of the coming few months. So expect to be foiling within the next couple months here, and then flying in the spring.
Oh, excellent. Yeah, yeah. And I guess we're in the zeitgeist where hardware companies, actually testing pretty hard and testing their products to breakage just to make sure they learn the maximum amount of things they can out of the testing campaign. Yeah, looking at the bigger rocket companies and how fast are they developing.
It's just critical, as we mentioned earlier, that the control system is only good if you can define it across the full envelope. And so it is absolutely our responsibility, with human crew on board, with human passengers on board eventually, to ensure that our controllers are robust and ready for that real world safety case. So this is all part of your typical test campaign. We plan for that. We keep spare parts for that. That's why we were able to go from that event and get back on the water within 4 weeks. That's why no one was harmed throughout that test. We only subject the vehicle in the test campaign and the crew to risks that we know stay within our safe operational window, and it's very crawl, walk, run, and stair step. So, Elon's blowing up rockets, and you can do that when there's no one on board. But when there are people on board, we have that additional responsibility. Testing takes a little bit longer, but that is the mission, right? We have committed to our customers and to our investors and to eventually everyone who's taking a Seaglider and trusting themselves and their families to it. Regent has made this commitment of safety.
Yeah, because I really want to see this happening, this succeeding, because it's so excited that a company, a ground effect company, is actually having a good engineering team and a good marketing team. In the past, there were either engineering teams or the really good at engineering parts, but they couldn't sell the craft, or the really marketing teams that actually just sold some vaporware. So it's really exciting to see this happening. So your view on, you are going through the testing campaign. The Seaglider will be flying, right, in the next few months, hopefully, fingers crossed.
Yeah.
You'll do a bunch more testing. You'll do production. The first Seaglider comes off the line. Who is going to sit in the Seaglider, and how are you making sure that the public knows that these things are safe? Because we've never seen them before. Imagine a person looking out on the water and seeing the Seaglider, zipping past at high rates and maybe taken aback a little bit.
Yeah. Well, very importantly, we will have third-party certification and validation for this. And so in the US, that's working with the US Coast Guard as the certification authority. Internationally, that's working with both the flag regulators of each country, so that the National Maritime Regulator, but also internationally with the IMO, the International Maritime Organization, and with Lloyd's Register, a classification society, which gives some international extensibility of that certification, and many countries actually delegate full authority to Lloyd's Register. So pretty excited about that. Last point I'll make here is just actually when you're out there testing and then you sort of start driving away a little bit. Well, it looks like a very large craft in person. It is. It's 12 passengers. It's going to be the largest electric craft ever to fly. But as you start sort of driving away from it, say on the water, it really does shrink into the maritime world, and you even have a problem sort of picking it out at distance and even moving it at relatively high speeds. Whenever it's in the harbor, it's hydrofoiling. It's a boat like any other boat, and then we save that high speed takeoff flight regimes when we're in open water, and we really do have a lot of room. Great to catch up, and great questions too.
Okay, thank you very much, Billy.
Awesome. All right, see you,
Thanks for
Paul.
coming on the show. Cheers. Bye.
Bye.